Okay, so in this video, I'm going to be talking about osmosis, so touch on a bit of biology. But for the most part, I'll be talking about osmotic pressure and problems dealing with osmotic pressure. Alright, so let's think about this right here. Don't want to talk about too much because that also touches into physics and yeah. Anyway, so we have, let's say this is a more concentrated solution. More concentrated of solute. Alright, so this doesn't have very much water molecules compared to this. Alright, this one has less. And this yellow line right here is our semi-permeable membrane. And what is osmosis? It's just a process of filtering out certain things using a semi-permeable membrane. I mean, that's what our intestines do, and pig intestines, I believe. And it's not just that. Like, it's a main focus in biology. Now, it's done with chemistry, but, you know. But anyway, the pressure on both sides here are unequal because there's a lot of water molecules here. There's not that many water molecules here. So the weights are different than in physics. The weight of gravity on both sides are different. Or not the... Well, the rate of gravity is the same. It's just the forces that they're both exerting are different. And with fluids, yeah, it's just even more complicated. But the pressures on both sides are different. So in order to exert an equal amount of pressure on both sides, the forces on both need to be equal. So the forces on both are equal, which means the weights on both sides are equal. Now, if the areas on both sides are different, then that's when we start getting into even more complicated stuff. But let's just assume that these tubes are identical and they're connected identically, so it's like the same. The circumference of the entire tube is the same throughout. It's uniformly. Alright? So if there's more water here and less water here and more concentrated of the solute here, water is usually not that big of a compound, right? So it's pretty small. So basically we can assume that water is going to jump into this one, causing this level to rise and this one to drop. Alright, so all this is osmosis. Now, the point of equilibrium, that's basically the osmotic pressure of both, that they're both exerting in order to keep it at that state. They're trying to dilute the solute here so it would be less concentrated. Maybe both of these end up equaling, but we can figure out the pressure on both of these sides individually as well if we know the concentration. Okay, but usually the osmotic pressure given is at equilibrium, so the concentration of both sides are basically equal. That's basically what they're trying to aim for. How do I know this? Well, I know the equation. Do you know the equation? Well, I'm about to give it to you in case you don't, even though you probably do at this point. PV equals nRT. Probably asking yourself, but wait, isn't that basically the gas equation? Well, I'm saying yes. But let's solve for P since we're talking about osmotic pressure. Divide both sides by V, you get nRT over V. That's basically the equation, right? And now you're telling yourself, but wait, we're talking about concentrations here. There's no molarity involved here. What about this? Isn't this basically molarity? Now, if you remember from the gas laws, pressure is in ATM, volume's in liters, moles is in, well, N is in moles, really. And then R is the gas constant with crazy units, and then T is temperature for kelvins, with the unit kelvins. So, moles over volume. That sounds familiar. That's right. It's basically molarity. So we can replace that. So now we can figure out the pressure on both of these at any point with the concentrations here at a certain temperature. However, we don't want to know that. We want to know And this is basically using gas laws for liquids, which I thought was, whoa. But anyway, this is the pressure being exerted on both sides at equilibrium, basically when the concentration of the solute is the same. The osmotic pressure is equal to the molarity of the solute, not the solvent, the solute, because remember, this is a colligative property, or however you say it. It's a property that is dependent on the concentration of the solute, not the type of solute it is. So molarity of the solute times the gas constant times temperature. All the same units as here. Okay, realize that they can play a trick on you here when using this. You might go, oh, okay, this is pretty easy. Don't think that. I made a couple of mistakes doing that. I'll show you what I did wrong in another one.